linear momentum. So now this is not necessarily true in, well, certainly we know how to replace this with operators, how to replace this with operators, right? So actually we can just simply write down the, by using a quantum classical correspondence, we can simply write down the operators for the angular momentum in quantum mechanics. But that is not necessarily the operators, if we have to rely on classical quantum correspondence. So what doesn't change when we go from classical physics, which is the scale of big things, to quantum mechanics, which is the scale of small things? What doesn't change? Dimension never changes. Right? What is the dimension of angular momentum?
Second? Joule second?
Yeah, it's joule second, right? Why is it joule second? Okay, so we have meters times momentum, right? Momentum is what? Kilogram meters squared per second, right? This is joules, right? No, meters per second. Yeah. This is joules, right? To give 1 kilogram, the acceleration of 1 meters per, so to do work for the 1 Newton for 1 meter, so, and then times seconds. Okay. So this is, joule would be second squared, right? So this thing is, if I square it here, this is joule times second. What is joules times second? Okay. This is action, right? Remember our Lagrangian was energy integral over time. Okay. So angular momentum has the unit of action. And what is the unit of action in quantum mechanics? It's h bar, right? Okay. So it's no wonder that when we actually did the explicit differential equations in the spherical and cylindrical coordinates, that the angular momentums were quantized. Okay. Because they have the unit, they have the same dimension as h bar, and if anything should be quantized, it should be angular momentum, because they are a measure of action. Okay. So you should remember this. From purely dimensional analysis, we sort of see that beforehand that angular momentum should be quantized in quantum mechanics. Okay. So now, instead of writing down, for instance, LZ, if I go from here, the operator LZ would just be x p y minus y p x. So instead of starting from here, let me show you why it must be this. Okay. And let's, instead of considering classical quantum correspondence, let's think about how systems rotate when I rotate them about the z-axis. So we restrict ourselves to the xy plane. And this coordinate system has the z coming out, right? So a counterclockwise rotation is modeled by some angle here, right? So let's see, suppose I had a point P of xy, okay? And I apply this rotation to it. After the rotation, it goes into P of x prime, y prime, right? And let's find the transformation between xy and x prime, y prime. Okay. So how do we do that? It's very easy to figure out how a point on the x-axis gets rotated. Right? So, but every point can be decomposed onto the x and y axis. So let's think about the rotation from the x-axis first. So this gets rotated to here, and this is an angle phi. Okay. So originally we had x. Okay. And now we have a mixture of x and y. So x0 after a rotation, I'm going to denote this rotation by an operator u. Okay. And I'm going to label it by the angle that it rotates. Okay. Phi. Okay. And why do I use u? Because beforehand we're going to say that the rotation must be a unitary operator. Because rotation never stretched anything. Right? So area is conserved under rotation. And what is area in 2D? It's just a probability density, right? So it must be unitary. So this goes into what? the x-axis is shortened by cosine phi, right? So x cosine phi, okay? And the y component picks up sine phi, right? X sine phi. Okay, so that's how a point on the x-axis is rotated. Okay, now for the y-axis is also very simple. Right? Phi, okay, 0, y under this rotation by phi goes into what? X-axis picks up a minus y sine phi, right? And then the y-axis is shortened to y cosine phi. Correct? Okay, so now I can build a transformation between going from x and y under this rotation about the z-axis by phi. This is just given by the transformation matrix is just cosine phi sine phi minus sine phi cosine phi, and this gives you the prime coordinates. Correct? Did I get the sign correct here? Yeah, I think so. Right. So now we can think about what is the point in the xy plane in terms of Dirac notation. Let's use Dirac notation. It's just the position eigencat, right? So a point, okay, is just let me say a point at x and y. This is like a position eigencat because it's like a delta function eigenfunction, a wave function located at a point x and y. Okay. So now what is the action of this operator u on the position eigencat? It changes into a different position eigencat, right? So u phi x and y is equal to, let's write this. Okay. So x goes into cosine phi x plus sine phi y, right? And then the other one is cosine phi y minus sine phi x. Okay. So this operator rotates this position eigencat into a new position eigencat. Okay. Correct? Alright. So now we're going to consider infinitesimal rotation. Okay. So let's think about, okay, so I've already said to preserve probability under rotation, we need this operator to be unitary. What are the other properties it should have? So now infinitesimal rotation by an angle of epsilon.
I think you got the sign wrong.
I did.
Yeah.
So let me check. Okay. I think I might have two. So, yeah, thanks. Right, this is minus, this is plus. Just to do the
You might like to write a little bit bigger because the family may not be very wide. It's too small.
Oh, okay.
Infinitesimal rotation.
But I think I spelled infinitesimal wrong, so I don't want to write
And that's way small.
infinitesimal. Is this the correct spelling? I think so. Okay. Anyways, that's not important. So first property is unitarity. So I'm going to write unitary, which is saying that the Hermitian adjoint is just its inverse. Okay. This is the identity operator. Okay. What's the second property? Well, first, if we rotate by a small angle first, and then we rotate by another small angle, we want the action to be the same as rotating by the sum. Right? So there is a special composition law. And then the third property is the limit. Okay. What kind of limit is this? In the limit of vanishing epsilon, okay, the rotation through a vanishing angle is just the identity operator. Right? So limit as epsilon goes to 0. This should be the identity operator, correct? Okay. So actually, there's also a implicit condition based on the composition law and the unitarity, right? So if I think about u epsilon 1, u minus epsilon 1, by composition this should be the identity, right? So and of course this is true for unitary algebra. So actually the Hermitian adjoint of this is just minus, okay? Correct? So now let's be imaginative. Okay? And I'm going to say that all these properties are satisfied if I write the infinitesimal rotation through epsilon by I minus I, and I can use whatever operator I like, and I'm going to call it LZ. Okay. So why do we write it in this form? First of all, the limit is trivially satisfied, right? Okay. And then you can check that because of this composition law, it tells us that if we were to make a power series expansion, okay, of u in terms of epsilon times some other operator, it must be linear in epsilon because of this composition thing. Right? We put the I here. Actually to satisfy the unitarity condition, and then to make this operator a Hermitian operator. Okay. So now that we've constructed it this way, this is an operator, a Hermitian operator that produces rotation. Okay. What is that? It must be angular momentum, correct? Because that's what angular momentum means. If I have angular momentum, I'm going to cause rotation. Right? If I have translational momentum, I cause a displacement in the x direction, right? So that's what angular momentum means. They are the generators of rotation. So it's natural to put LZ here. Okay, so and this is the angular momentum in the z direction. And now there's a problem. This is unitary. This thing must be dimensionless, right? Well, we know that angular momentum has a dimension of h bar. So let's scale this by h bar. Okay. So this is our infinitesimal translation and rotation operator. And you can check these properties on their own. They're quite easy. Okay. So all these properties are correct to first order in epsilon. Okay. So you're going to get second order terms here. We just neglect them because of calculus. Okay. So now let's consider what happens to a wave function after an infinitesimal rotation. Okay. So before, the wave function looks like this, okay. Right? Written in Dirac notation. Okay. You should be familiar with this notation by now. And now if I apply the infinitesimal rotation and then seek out what is its spatial representation, I would write something like this. Represented onto the xy eigen basis, and then infinitesimal rotation operator operating on phi. Okay. What is this? And so first of all, let's evaluate this algebraically. So I can say that, well, I don't know how this works on this, but I do know how this transforms a coordinate eigen ket. But this is an eigengraph. But that's okay. This is equal to this is equal to the Hermitian adjoint of this. And then I need to take the right? Right? Okay. We just said, what's the Hermitian adjoint? It's just its inverse, and by composition law, it's just the rotation in the other direction. So this is just u of minus epsilon and y. Okay. And now we plug in the formula here, right? Okay. So because epsilon is small, we use small argument approximation. Cosine epsilon goes to 1, sine epsilon goes to epsilon. Okay. So this turns into cosine is just 1, right? So x. And then minus sine epsilon is, because it's a minus epsilon, it goes into plus epsilon y. Right? Okay. And then cosine is 1 again, y. And then plus sine minus epsilon, which is minus epsilon. Okay. So minus epsilon x. Okay. So and then we need to compute the aggregate of this thing, which just turns this into the bra, right? Okay. So now that thing turns into x plus epsilon y. Y minus epsilon x y, which is equal to phi of x plus epsilon y, y minus epsilon x. Okay. So you notice something interesting. Although an eigenbasis, an eigenket, is rotated this way, a function is rotated the other way. And why is that? This should be most obvious, because before the rotation, right? Let's think about that picture again. Okay. This picture over here. Suppose now that each point P and P prime is assigned a value. Okay. So the rotation, the action of the rotation is to replace the value at P with at P prime with the value at P. Right. So before the rotation, we can write phi at P prime. Okay. And then after the rotation, this is replaced by phi at P. Okay. So that means for a function, okay, the prime gets rotated into the unprimed system. And if you look at the argument, you apply the inverse operator to this. Right? And this is 2 by 2 matrix. Okay. Certainly this is invertible. How do you invert this? Okay. You write cosine phi plus sin phi minus sin phi. Right? And then you divide by the square of the determinant, and this is determinant is 1. Okay. So should be clear. Okay. So remember, because we are representing a function onto the eigengraph, so the function, the argument of the function actually transforms as a graph, not as a cat. Okay. So the rotation is in the opposite direction. And this is extremely important because now we can think about what is the difference between these two. Okay. So on the left hand side, I can write phi of xy minus phi of what was it? X plus epsilon y, y minus epsilon x. Okay. So what am I going to do next? Just Fourier, not Fourier, Taylor expansion, right? Always do Taylor expansion. Well, but on the left hand, on this side, this is this minus this. Let me write this as the identity operator in the middle. Okay. So this is x, y with the identity operator in the middle, y, minus, and let me write this infinitesimal rotation with this operator we have found. Minus x, y, identity minus. Okay, so there's some cancellation on the right hand side, right? The identity operator cancel. Okay, and we're left with I over h bar epsilon s y l z. Correct? Okay. What about the left hand side? After doing Taylor expansion, expand this part, right? This is phi of x, y, okay? and then plus epsilon times d phi dx, right? And then it's epsilon y times d phi dx, right? Because the small amount that we change is epsilon y. And then over here, this is minus epsilon x d phi dy. Okay? And then there's phi x y subtracting this whole thing from it. Okay? So again, we get some cancellations. Right? So this turns into epsilon times, okay, minus turns into a plus. Okay? X d dy minus y d dx operating on phi. Okay? So what is this? What does this mean? Okay. This is just the coordinate representation of the operator LZ operating on the function, wave function phi, which is this side. So we read out from here by canceling the epsilon. Okay, we read out from here that the coordinate representation of LZ is just x hat. Okay, h bar over I d dy minus phi with coordinate representation. Let me write this explicitly. Okay. Y h bar over I d dx. Okay, so now if we forget about coordinate representation and we turn this into a product, a combination of operators, this is just xpy minus ypx, right? Right? Okay. So we get that actually in classical physics and quantum mechanics, they do actually, the angular momentum operator actually do respect the classical quantum correspondence. And the reason for that is not because any link between classical and quantum physics. It's because angular momentum, the fundamental physics of angular momentum is here. Okay? It's in the rotations. We derived it from rotations. So you should say that in classical physics, the angular momentum looks like this because in quantum mechanics, you should go this way, not the other way around. All right, so this is, so now we derive this, and since there's nothing special about the z direction, we can go ahead and write down by cyclic permutation of x, y, z, right? You can write down everything. I'm not going to bother writing that. And we're pretty safe to say that anything having to do with angular momentum, we can just use the classical expression and replace it with the operators like this, because it works. Is this Hermitian? We've assumed LZ to be Hermitian. This is certainly a Hermitian, because if I were to put a dagger here, Py and X commutes. So there's no difference in image, and they are all Hermitian. So this is obviously a Hermitian operator. Okay. So what time is it? Oh, we still have some time. So now, let's think about, so far, what we have done is we have thought about the angular momentum as a generator of rotation. Right? And by thinking about infinitesimal rotation, we derive its coordinate representation. And to get finite rotation, you just compound infinitesimal rotation. So far, what's the difference between angular momentum and translational momentum? There's not much, right? You can also do this analysis, this whole analysis with linear momentum, and it'll work. You always make assumption that the infinitesimal translation is caused by the generator goes into the translator. Okay, so it's always like this. So in the math, there's no difference. But physically, we can think about what's the difference between rotation and translation. Right? So if I'm standing here and I have a px momentum, I'm going to go over here. And then I have a py momentum, and I'll go over here. So translation takes me here. X translation and Y translation takes me here. But If I do it the other way, y translation and x translation takes me to the same place. Right? If I do this, just a parallel. What's this called? Yeah, a rectangle. Right? But rotation is very different. Let's just consider a line, and it's in the x, y, and z coordinate. Okay. Let's rotate the line, okay, with respect to coordinate system in itself. So the central mass is here. Let's rotate it in the y direction first. So that takes us, rotation in the y direction by pi over 2. Okay. Positive y direction is this way. So we rotate in this way. Present to something like this. And then we rotate it in the x direction, nothing happens. Okay. We are left with this. So after a rotation in the x direction of pi over 2, which is in this way, nothing happens. So we're left with this. Okay. But now, if I started with a rotation in the x direction, okay, I get this. Right? Okay. And then after I turn it with a rotation in the y direction, nothing changes. Right? I get this. So rotations do not commute. Okay. And we should see to it that our operators build in this non-commutativity of rotation into it. Okay. And we can check that most easily. Just do the algebra. Okay. So I do actually have to write down the component. So let's do cyclic permutation. And whenever you have x, y, z, you can always do this because something is related by cross product. So z goes to x, x goes to y, y goes to z, y goes to z, x goes to y. No brainer. Just cyclic permutation. So now let's consider what is the commutator between LZ and LX. Okay. So this is LZ LX minus LX LZ. Did you guys do this in the take-home exam? So you all know this is an IH bar line. IH bar LY. So good. Okay, so our angular momentum do not compute. And maybe you did the problem correctly. Okay, so the angular momentum operators don't commute. And this is true because rotations don't commute. Right. So now I can simplify the notation for you. Okay. Notice that over here we have IHR and x, y, z, x, y. They respect cyclic order. Okay. So x to y to z and back. Okay. This is z, x, y. So they're in the correct cyclic order, and you get a plus sign. Okay. So I can say that Li, Lj is equal to I H bar. And there's something called epsilon ijk. Okay. And the epsilon ijk, don't worry what it is. Just think about if ijk is in the correct or incorrect cyclic order. If it's correct, it's a +1. If it's incorrect, it's a minus. Okay. So you can just remember it this way. And then ijk takes on values of x, y, z. So that's one way to write it. Now, think about what we did in the spherical coordinate problem.
Since you don't have much time left, why did you talk about the non-infinitesimal rotation? You wrote down the U operator for infinitesimal rotation, but you never get to the rotation. The rotation is not.
For finite rotation, okay, we're going to do a finite rotation by using the composition law. Okay. So the finite rotation is certainly given by an infinitesimal rotation. I can divide this with into n parts. So I have a limit as my division goes to very fine. The infinitesimal rotation pi over n applied n times, correct? So now, because I'm taking n going to infinity, this is an infinitesimal rotation. Right? So let's plug that in is the identity operator minus I times epsilon, which is now replaced by phi over n, right? Okay, and then it's LZ over h bar to the nth power. What is this limit? This x is this is the definition of exponential, right? So this is just e to the minus I LZ over h bar phi. So a finite rotation is achieved by exponentiating the LZ. So if you have a generator of rotation, if you have a generator of rotation is just translation in an angular direction. So if you have a generator of some translation, then the finite translation is almost always given by the exponentiation of the generator. Okay? And what is this? Okay, you've seen this in Fourier transform. Remember, we always say, okay, Hamiltonian generates translation at time evolution. So because that's what Schrodinger equation tells us. Hamiltonian generates time evolution. So the time evolution operator is done by exponentiating the Hamiltonian. And that's time independent Hamiltonian. That's one case. And this really, it says that if I'm trying to translate in phi, okay, it's like adding a phase shift. This is a phase shift. So this is just Fourier transform. Right? You've seen this in Fourier transform. If I go from the x to p, right, and the momentum is the generator of translation in x, x momentum generator of translation in x. So now, if I exponentiate the momentum operator, that turns into a phase factor in x. Right? So translation in x turns into a phase shift in the momentum space. So this is, you've seen this in Fourier transform. And I would say this is a reason for it. Okay. Or you can take Fourier transform to be a reason for it. Right? So we have 5 minutes. Let's stop here. I'll continue on.
Okay.
It's Tuesday.
I thought you want to go and talk about the translational case.
Oh, sure.
I thought you were moving towards that.
No. Because translation we've already covered.
I don't think we covered.
We have already covered.
How do you use the p hat operator to create translation?
Okay, sure.
I
We
just
can.
wanted to use the last 5 minutes. Because it's very simple.
Yeah, but it's not necessarily very simple to write down. But okay, I'll do it. So. The case of linear momentum. Okay, so we start this by postulating that there is some translation operator, and we can work in 1D because this is translation. Okay, there's some translation operator given by t. Okay, and we denote the amount of translation by alpha. Okay, and if this acts on a coordinate eigencat, this turns it into x plus alpha. Okay. All right, and we say that this translation respects the same kind of properties, unitary, and so on and so forth, composition and limit. Okay. So the translation operator, and let's say that alpha is an infinitesimal thing. Okay. This is equal to the identity minus, okay, I, and then it's alpha, p. And I'm just going to use the Hermitian operator is going to be denoted by px. Okay. And let's think about the dimension. Okay. What's the dimension of alpha? Previously we had a rotation in terms of angle. Angle has no dimension, but now alpha has dimension. Okay. P has dimension. Okay. So of course we're going to use the translational momentum as the generator of translation. So P has, this is just h bar again, right? So divide by h bar. Okay. So now if I do the same thing, right, I think about how, So yeah, this is this. Now I think about how I represent function. Okay, and I think about the difference of this. Okay. And then I Fourier expand, Taylor expand. Okay. And I'm going to get, because this is only in 1D now, I'm just going to get the partial derivative with respect to x. So that's why the momentum operator has the expression in the coordinate in the coordinate representation. The expression for the momentum operator is I h bar over I dx. Okay, so they're all the same. And also you could say that this is also why the Hamiltonian for the simplest case is equal to I h bar dt. There's a sign difference here. That's actually a very deep question. Why is there a sign difference? So yeah, that's it. Okay. So next week we're going to talk about the spectrum. We didn't finish today. The spectrum of the angular momentum, and this spectrum is actually shared by spin and angular momentum. So we're doing chapter 8, chapter 9 together. Okay? And then explicit coordinate representation is finding the eigenfunction.